Hello everyone and welcome to the first problem video of the semester. So these are usually shorter and I don't usually have things written out beforehand and I just write the problems as I go through them. So maybe my handwriting will be a bit sloppier than in the lecture videos and I might make mistakes. So don't take my word as law. In normally during the lectures when life is like it was back in for pre-pandemic days. I would lecture on the board and I would make some mistakes and people would point them out to me and I'd say, "Oh yeah, sorry about that. This should be that." Obviously, I don't have you guys with me here at home to point out my mistakes, so some of them might slip through the cracks. Feel free to message me if you like, if you see a mistake, but don't assume that if something doesn't make sense, perhaps it is possible I made a mistake. So I'm not infallible. So these problems are coming from the textbook, section 5.4, and I'm just going to do several of these problems. First up would be number 6. So this integral here, the fourth root of x to the power 5 dx. And all of these problems are going to be solved just using the table on page 403 of the textbook, I believe. Yeah, page 403. That table of indefinite integrals, these are just going to rely on the basic rules of integration. So this is going to be a power rule. Okay, when we see something like this, what we're going to do is we're going to rewrite this as a single exponent. So the fourth root of x to the power 5, that's the same thing as x to the power 5 over 4 dx. Now that it's in this form, we can see easily that, okay, this is going to be a power rule. So we're going to add 1 to the exponent, and we're going to divide by that number. So let's see. Okay, so now we're just going to simplify. Let's see, x to the 5 over 4 plus 1. Well, 5 over 4 plus 1, that's 9 over 4. And then we're dividing by 9 over 4 as well. And remember, when we divide by a fraction, that's the same thing as multiplying by the reciprocal. So this should be our antiderivative. And since our original problem was an indefinite integral, meaning we didn't have any bounds on our integral, the answer we're looking for is just a function, an antiderivative, and we have the plus c, our constant of integration. Another good one is number 8. Okay, this is good for a couple reasons. Number one, we're not always going to be integrating in terms of x. Maybe our integral, so in this integral we have functions of u, and we're integrating in terms of u. Okay, so the variable inside the integral doesn't matter too much as long as it's the same throughout the integral. We don't want to mix, not in this course. In Calc 3, you might see something different, but in this course, we're just doing everything in one variable. So there should only be one variable inside my integral. Okay, so in this case, it's u, so I don't want to see any x's or anything like that in there. All right. In order to deal with this, what should I do? Well, I have one function, this u plus 4 times another. Okay. We'll see in the next section that this presents problems sometimes, but sometimes what we can do to deal with these is just multiply out these functions. So if we multiply out these two functions, so multiply this by this and just multiply everything out, what do I get? I get 2u squared plus u plus 8u plus 4, right, du. Let's just simplify that. I get this. Okay, now each of these terms individually I can integrate, right? So that's all I need to do. I just need to integrate these terms. again, this comes down to power rule, basically. Okay, and that would be my answer for that one. Number 10 and number 11 are similar. Okay, so let's say I have number 10. I have, let's see, integral square root of t times t squared plus 3t plus 2, integrating in terms of t. So maybe this seems complicated at first. I got a square root of t here, and then I got this polynomial here. But again, I can just multiply all this out. Okay, maybe it's not as clean as in the previous case. Up in number 8, I only had integer exponents, so whole numbers in my exponents. Now I'm going to have some fractions, right? So maybe it'll be more clear if I write square root of t as t to the 1/2. Okay. Now just multiplying out, and when I multiply one number with an exponent times another, I just add those exponents together. Okay, so when I multiply these out, I get t to the 5/2 plus 3t to the 3/2 plus 2t to the 1/2. And then it's just power rule again. So my answer should be this. Feel free to, I might have made a little mistake in this mental math on these, so feel free to check me, but the exponents should be right, and that looks good to me. Okay, let's see number 11 now. Okay, I have 1 plus square root of x plus x all over x dx. Okay. Oh, this problem raises a good point. I'll cover in the next example. Okay, so I can basically just divide each of these terms in the numerator by x. Okay. We got to be careful how we split up fractions, right? If I have, this is not connected to this problem, just in general. If I have ax, or let's even keep it more general. Let's say I have a over b, or a plus b over c. Okay, this is going to be equal to a over c plus b over c, right? That's good. What I can't do is if I have a over b plus c, well, I can't split that up as easily, right? We're actually going to cover this scenario in section 7.4. So this is something we're going to deal with later in the semester. But keep in mind that, okay, if we have a fraction like this, yeah, we can split it up into these, but we can't split this thing up as easily, okay? Okay, so back to our problem. How do I deal with this? Well, I'm gonna split these up into 1 over x plus square root of x over x plus x over x. You might see me putting parentheses around stuff inside the integral. Whenever we have terms inside the integral, like if I have terms inside my integral f plus g plus h, whatever, I want to enclose everything in parentheses and then have dx. That's just a notation point. It's not a huge thing. In fact, I did this wrong I didn't have these parentheses for several years. It's something I only started doing recently. So it's something that slips through the cracks, but try and be better than me. Try and start doing parentheses now. Okay. So let's see. What's the integral of this thing? Since I have plus, since everything's added together, I can just do these parts individually. Okay. So what's the antiderivative of 1 over x? From my table, I know that's ln absolute value of x. This absolute value, that's important. So keep absolute values in that ln. Okay. What's square root of x over x? Well, this is going to be x to the negative 1/2, right? So what's the antiderivative of that? Should be this. And then, well, this simplifies as 1. What's the antiderivative of that? That's going to be x. And then we have plus c. Okay, so I skipped some steps in simplification, but see if you can recreate this. And that should be the final answer. Okay. 12, we see something a bit new. Okay, let's go ahead and try and integrate this. Integral of x squared is x cubed over 3 plus, what's the integral of 1? That would just be x. And then what's the integral of this? 1 over x squared plus 1. Well, from my table, you might be able to see that this is going to be the integral. The integral of this is going to be the function tan inverse of x. Okay, tan inverse is, you could also write that as arctan, same thing. And I think this is maybe becoming more in style because tan inverse can be a bit ambiguous what you actually mean. So either one of these is acceptable. I always write tan inverse, but I think it's becoming more in vogue to write arctan. Okay. So this is the final answer. All right. So that covers most of, well, let's do one more indefinite integral. How about 16? We got some trig stuff. Secant of t times secant t plus tan t dt. Again, I have one term multiplied by this bigger term here. It's going to make my life a lot easier if I go ahead and multiply everything out. Okay. So I have the integral of secant squared t plus secant t tan t. Well, again, now I can do this piece by piece. Secant squared, integral of secant squared, well, that's going to be tan t. And then integral of secant t tan t, that should be secant t, I believe. And then I have my constant of integration plus c. So we're seeing some trig stuff now. Now let's try and do, these have all been indefinite integrals. Let's try some definite integrals. Just do a couple of those. This is, let's do 33. Okay. First step is just finding the antiderivative, just like I would with the indefinite integral. Okay, so I just integrate these term by term. Okay, so what's the integral of x over 2, the antiderivative? Well, let's see, it'd be x squared over 2. That's the integral of just x, and then I still have that 1/2. Okay, and then let's see, what's the integral of 2 over x? Let's go over here for a second. 2 over x dx, that is equal to 2 times integral of 1 over x dx. Integral of 1 over x is ln x, and I got 2 out front. Okay, so this should be minus 2 ln absolute value of x. And then instead of having the plus c, since I'm doing a definite integral, I'm going to have from 2 to 1. Okay, let's just simplify this a bit. I have x squared over 4 minus 2 ln x from 2 to 1. Okay, what is that? Let's see, I plug in 2, first of all. Okay, and then I subtract what I get when I plug in 1. Okay, and now I simplify. Well, 2 squared over 4, that's going to be 4 over 4, which is 1, minus 2 ln of absolute value of 2. Okay, minus 1/4 minus, and then what's ln of 1? Ln of 1 is 0. So I have minus 2 times 0, which is 0. Okay. Simplifying, I have 1 minus 2 ln of 2 minus 1/4 equals 3/4 minus 2 ln 2. And that should be my final answer, barring any mistakes on my part. Let's do one more definite integral. How about number 28? So 2 to 1, excuse me, 1 to 2, 1 over x squared minus 4 over x cubed dx. Okay, let's see, doing this term by term, let's see, the antiderivative of 1 over x squared, that's, well, x squared is, 1 over x squared is x to the negative 2. Let's just rewrite our integral in this form. Okay, my integral is equivalent to this integral. Okay, and now maybe it's clear how I integrate this. Power rule. Oh, and there shouldn't be an integral there, or integral sign. I need my bounds. Okay, let's go ahead and simplify this. Okay, and now let's evaluate at our bounds. Okay, negative, let's see, negative, I got my negative sign here, then I got 2 to the power of negative 1, so that'd be 1 over 2, plus 2 times 1 over 2 squared, okay, minus negative 1 over 1, plus 2 times 1 over 1 squared, okay, simplifying. Let's see, this term is going to be equal to 1/2. All right, so I got minus 1/2 plus 1/2 minus, let's see, negative 1 plus 2. Okay, so that's 0. This term 0 minus negative 1 plus 2. Okay, well, let's see, this is positive 1. So I have minus positive 1. So my answer should be negative 1. All right. So we've solved several problems. I don't see any here in the chapter that are significantly trickier. except maybe let's do one more. Maybe some of this trig stuff is a bit trickier. Well, number 37, 0 to pi over 4, 1 plus cosine squared theta over cosine squared theta d theta. Okay, how could we split this up? Let's see. Off the top of my head, I would say to split this up like so. Okay, I would split it up as 1 over cosine squared theta plus cosine squared theta over cosine squared theta d theta. Okay, let's simplify. Okay, so I have this integral. Now, the key to this one would be recognizing that what is 1 over cosine squared? 1 over cosine squared is the same thing as secant squared theta plus 1. Okay. And then what's the integral of secant squared? That should be tan squared. No, just tan. Excuse me, tan theta. Okay, and then what's the integral of 1? That's just theta. And then I'm evaluating from the bounds pi over 4 to 0. So this one, we might see some trig identities in the homework. So keep those in mind as well. Evaluating, let's see, tan of pi over 4, that's 1 plus pi over 4, okay, minus, okay, what's tan of 0? That's 0 plus 0, okay. So I should have pi over 4 plus 1, which is the same thing as, let's see, pi plus 4 over 4. So that should be our answer for that one. Okay, I think that's a good number of examples, so I will stop there.